In this abstract algebra tutorial, I'll be giving further examples of groups and to do some properties about groups in general. In our first example, the set of 2 by 2 matrices with real entries under matrix multiplication is considered. As a reminder, here is 2 by 2 matrix multiplication defined algebraically. Given that the real numbers are closed under addition and multiplication, and looking at the definition, it is clear that the algebraic structure is closed. In the case of 2 by 2 matrices, matrix multiplication can be proved to be associative by direct algebraic computation. So we have a semigroup. It is useful to note that matrix multiplication in general is associative, and that the proof is readily found in most linear algebra textbooks. The 2 by 2 identity matrix shown here can be proven to be the identity of this algebraic structure by affirming so through algebraic computation. So we have a monoid. The inverse of a general 2 by 2 matrix is shown here. The number AD minus BC is called the determinant of the 2 by 2 matrix and is denoted in this way. It can be seen that if the determinant of a matrix is 0, then the matrix does not have an inverse. So the monoid is not invertible and so is not a group. If, however, we consider only the set of invertible 2 by 2 matrices under matrix multiplication, then we will have a group. This very important group is called the general linear group of degree 2 over the real numbers, and is denoted in this way. In our next example, we consider the set of all 2 by 2 matrices with a determinant of 1 under matrix multiplication. A general result from linear algebra is that the determinant of a product of matrices is equal to the product of the individual determinants. We can use this fact to show that the product of two matrices from the underlying set will also be a member of the underlying set. So we have closure. Notice how the underlying set in this example is actually a subset of the underlying set used in the previous example. So we don't have to check for associativity. The underlying set also contains the identity matrix, which has a determinant of 1. So we have a monoid. All the elements of the underlying set have inverses, but it remains to prove that the inverses are members of the underlying set. We again appeal to general results from linear algebra. As the determinant of a matrix is a reciprocal of the determinant of the inverse of that matrix, then the inverses of members of the underlying set are themselves members of the underlying set, and always exist. So we have a group. This group is called the special linear group of degree 2 over the real numbers, and is denoted in this way. Before moving on to our last example, an important distinction between two types of groups is restated. You may have noticed that some groups discussed are commutative and others are not. A commutative group is called an Abelian group in honor of Niels Abel. One of the foremost mathematicians of the 19th century, whose research laid the groundwork for the development of modern abstract algebra. The integers under addition is an Abelian group, whereas the previous two groups are non-Abelian. Now we consider the set of three-dimensional vectors under vector addition. Any vector can be represented uniquely in its component form, and the addition of two vectors is defined by component-wise addition. Based on this definition and the given properties of real numbers, we deduce that the algebraic structure is both closed and associative. The null vector is the identity, and every vector has an additive inverse. So we have a group. In this case we have an abelian group, as addition over the real numbers is commutative. Now we prove that the identity of a group is unique. From now on, instead of saying A operated on B, we will say A times B when we are talking about groups and making arguments about them in general. Suppose that a group whose underlying set G has more than one identity and that two of them are denoted E and E dash. Then A times E is equal to A for all A and G, and E dash times A is equal to A for all A and G. Substituting E dash for A in equation 1 and E for A in equation 2, then we can immediately see a new equation that E dash is equal to E. So we may unambiguously speak of the identity of a group. This theorem is useful because it means we only have to search for one identity. Also note that proofs in mathematics are conventionally ended with a solid black rectangle. Now we prove that right and left cancellation laws hold in a group. Suppose that for a group that A times B equals A times C, multiply both sides on the left by the inverse of A, then use the property of associativity and the definition of an inverse element to reduce the equation to E times B equals E times C, then by the definition of the identity element B equals C. The right cancellation law can be proved similarly. One consequence of this theorem that we will see in the next video is that in a group table, each element of the underlying set appears exactly once in each row and column. Finally, we prove that the inverses of elements in a group are unique. Suppose that an element A has more than one inverse and that we consider any two of them, calling them B and C. Then A times B equals E, and A times C equals E. So A times B equals A times C. Then using theorem 2 we cancel on the left and see that B equals C. So we can speak of the inverse of an element. Before moving on to the next video, try practicing the concepts with the following questions. Prove that the set of rational numbers of the form 3 to the m times 6 to the n, where m and n are integers, is a group under multiplication. Prove that for all groups the inverse of A times B is equal to inverse B times inverse A. Prove that if you have a group G such that for all A, B and C belonging to the underlying set of G, that A times B equals C times A implies B equals C is true, then the group G is abelian. Finally, find an example of a group such that inverse A times B times A is not equal to B. Okay, thank you for watching.